All right, good morning, everybody. We're going to go ahead and start with our Explore 4. So let's go ahead and draw out our lines. And today's date is 10/23, Monday. And the essential question in green, how are frequency and wavelength of electromagnetic radiation related? How are, plural, two things we're comparing, how are frequency and wavelength and we're talking about electromagnetic radiation of related, question mark. Okay, I guess I can just kind of carry out this line here a little bit. And let's start with Roman numeral 1. Okay, so the electromagnetic spectrum. We've shown this picture to you multiple times in class, everything from radio waves to TV waves, your cell phones, microwaves, ultraviolet, visible light, X-rays, gamma rays. All of these constitute the electromagnetic spectrum. It is the full range. Okay. It is the full range of, and here's maybe the key part, electromagnetic radiation. Maybe we'll underline that, okay? Just to draw our attention to that. Okay. Now, I guess if you wanted to sorry about that. If we want to get over here and examples, i.e., let's just put down i.e. Radio, TV, visible light, infrared / ultraviolet, X-ray, gamma ray. Right, those are some examples. Now here's the key part here. We're talking about the relationship, right? That's what we want to focus on. How are they related? Okay. What are we talking about? We're talking about frequency and wavelength. All right. So in paragraph 2, it says energy and frequency are directly proportional. So let's talk about some relationships here. Maybe we should give ourselves a little bit of background knowledge here. Let's go ahead and draw a y-axis and an x-axis. And we can say that a wave, a typical wave, demonstrates something like this. This is a little bit of review. This is the crest. This was the trough. And this was one full wavelength. Is one wavelength. And we also had something called the amplitude, right? The height of your wave. And if you recall, you could have something that looked like this, where if we drew something like this, we could say that in 1 second of time, we're going to just use that as our, this would be 0.5 seconds, you could have a okay, 2 waves per second versus, we could say something like this, 1 second. This was versus 1 wave per second. The question would be which one has the higher frequency. This one has a higher frequency because more waves per second, which means it's also going to deliver more energy. So let's, now that we've kind of given ourselves a little bit of background, let's come back over here. Energy and frequency are directly proportional. That makes sense. The more waves you have per second, the more energy is going to be delivered. That's relationship number 1, okay? Letter C. Energy and frequency are directly related, are directly related, okay? They're proportional. Now the second, and we could as easily over here just kind of draw that number 1. And number 2, energy and wavelength. So that's different. Energy and wavelength are inversely proportional to each other, okay? At lower energies, light has longer wavelengths, okay? And relation number 2, energy and wavelength are what we call indirectly, or what we could say is inversely. You should be comfortable with however it's described, indirect or inverse. They're synonymous. Inversely proportional. Okay. That just basically means as one goes up, the other one goes down. If energy increases, then the wavelength has to decrease. If energy decreases, then the wavelength has to increase. Okay. So this has a long wavelengths, lower energy. Okay, so let's keep moving on here. Wavelengths and frequencies can vary greatly. Consider the following examples. Read this, but you can see in here I've highlighted a few things that were interesting. First, under certain conditions, elements emit light in or near the visible light spectrum. This type of radiation has a wavelength about the size of a single bacterium. That's kind of interesting. The light you're seeing, the visible light, has a wavelength that's about the size of the diameter of a bacteria. Okay, perspective. Also, this other interesting part, gamma rays are emitted during nuclear changes. Okay, so when you take a look at the electromagnetic spectrum, the most energetic, most damaging, the most dangerous radiation is gamma rays. And those are generated through radioactive decay. Okay. And their wavelengths are shorter than the radius of a hydrogen atom. So we're talking very, very small. Very small. small wavelength equals increased energy, right? Okay, just to kind of keep that in our minds. So wavelength and frequency. As a form of electromagnetic radiation, light has properties that can be described as both waves and particles. All right, so let's go ahead and add that. Niels Bohr kind of had come up with that idea. Einstein wasn't too thrilled with it, but he managed to live with it. So we're going to call this letter D, okay? Wave, length, and frequency. And we're going to say number one, light can be described as both waves, and for the most part, we usually describe it that way, as waves and as particles. Okay. As you can see here, this duality is the best way to describe the behavior of light, but in many situations, its wave-like properties provide the most convenient description. Let's go ahead and keep moving on here. Wave frequency, and let's see here. Let's start from the beginning. This characteristic is known as wave frequency. That is how many times a wave passes a point in a given unit of time. So if you take a look at our original notes here, we said on this bottom one, it had a frequency of 1 hertz, right? And in this second image up here, we said that this one has a wave frequency of 2 hertz because there's 2 waves per second. Which one had the higher frequency? It was the 2 hertz, okay? And I think what we want to write here is that wave frequency is given by the symbol nu, okay? Okay. Wave frequency is described as equals, which is what we call nu. Okay, this is a symbol, and pronounced as nu. Okay, this SI unit for frequency is the hertz, measured in hertz. Measure in hertz. Okay, which is equal to 1 cycle per second to the negative 1. Okay. All right. Or we could just say per second. The distance from peak to peak in any given wave is constant. This characteristic is known as the wavelength. Okay. So I think we already described that, but we'll go ahead and write that over here. B. It's described wavelength. And we use the symbol lambda symbol. And this is called lambda. And if we were to draw a wave, and you were to say this to this to this to this, you could say that from this point to this point equals the wavelength. Length. Okay. Or you could say from this point to this point is a wavelength. Or you could say from this point to this point is a wavelength. Okay, it doesn't matter. Okay, and finally, we have a formula here. We have that the frequency, these two characteristics are inversely proportional. As the frequency increases, wavelength decreases, and vice versa. The inverse of one is equal to the other. So we've got this relationship called nu is equal to c multiplied times 1 over lambda. Okay, c is the speed of light. Okay. As you can see here, we're just referencing the text here. Mu is the wave frequency. And lambda is your wavelength. And I think finally, let's just clear that screen there and keep on moving here. You probably want to make a note here that c, the speed of light, is equal to 2.9979 times 10 to the 8th meters per second. This is the speed of light. Okay, this is a constant. And let's see here. An interesting point that you may want to make a note of is that Planck's wave equation. Many elements emit light when they're brought to high temperatures, and this was mathematically represented by Max Planck. Okay, so we're going to call this letter D. Make that black. Planck. Okay, Max Planck related energy absorption to the frequency of light emitted. And he used the equation here, E is equal to HV, and E was the amount of energy absorbed. H is a constant. This is the Planck constant. Planck's constant, that's something you'd have to be given. It's just a number that doesn't change. And the nu, of course, is your frequency. Okay, and I think the last really interesting part here, it comes down to here, where you can go ahead and actually relate the two equations, where E equals HV, and you substitute V for C over lambda. And that is important, so let's just go ahead and write that down. E is equal to HV. Substitute this V for H. And what was the V? V, it was the speed of light